Alright guys, welcome back to your next video lesson. Today we're going to talk about solving some special cases. So today we're going to be applying graphing, substitution, and elimination to solve special cases of systems of equations. So let's take a look. Alright, so let's take a look at our first two examples. So here's what I want you to do. I want you to quick pause the video and I want you to solve these two systems, numbers 1 and 2. I want you to solve them in your notes by graphing. Okay, so pause the video right now. I'm going to give you guys a little time this time to actually pause. So pause the video, solve these two systems by graphing, and we're going to talk about what we see. So here we go. Pause, 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 pause. Alright, so let's take a look at them. So first of all, first problem here, number 1. We had our two equations, first of all, written in slope-intercept form, so we were good to go to graph right away. So graphing these two lines, the green one, 1/2 x minus 4, I started with the minus 4, then applied my slope of 1 over 2. Red line, I went plus 2, did the same thing, applied my slope of 1 over 2. Now what do we notice? Okay, you should notice that these two lines do not intersect. So remember, when we solve by graphing, the point where the two lines intersect, that represents our solution. So notice here, they do not intersect. They are what are called parallel lines. If you remember back to last chapter, we looked at the slope of parallel lines. Notice here, slope of the two lines are the same. So these two lines are parallel, meaning they will never intersect. So what does that tell us about our solution? Okay, well, we're going to talk about that today. Same thing in number 2. Now, number 2, you had to do a little extra work. Notice neither of these are written in slope-intercept form. So what I did first, this line I took up here in green, I got y by itself. So the first thing I did is subtract 5x to the other side. Then to get rid of the 3, I divided by 3. Kind of skipped over the work, but notice that's kind of what I did. So I got negative 5 over 3x plus 2. So I graphed that line here, plus 2. Applied my slope. Since it's negative 5 over 3, I went down 5, right 3. And I got my green line there. Same thing with the red. I had just had to divide by 3 to get y by itself. So I got negative 5 over 3x minus 1. Notice again here, just like the previous problem, we have negative 5 over 3 as that slope, negative 5 over 3 here. Different y-intercepts. We see that the red line here, okay, again, they are not intersecting. They are parallel lines. They have the same slope. So that's what we're going to talk about today. There's some certain instances where lines don't intersect, things like that, special cases of systems of equations. We're going to talk about what does this mean in terms of our solution. All right, so here's a quick kind of table. This is in your notes, so please follow along. So here's what happens. Up to this point, we've solved equations through graphing, through substitution, elimination. Here's what really happens. When we graphed, normally what we would get is one solution, shown here. When two lines intersect, that point of x comma y where they intersect, that represents the solution to the system. So what happens if we have, for example, what we just looked at, lines that are parallel? The lines that are parallel, they will never intersect. So what does that tell us about the solution to the system? So what does that tell us? If they don't intersect, well, that means there cannot be a solution. The lines will never cross. They will never have an x and a y value in common. So when lines are parallel, what that tells us about the system is that there's no solution. There is no value of x and there is no value of y that each equation would have that would hold them true. Okay, so that represents no solution. The other thing that we could end up finding too, and this is kind of another special case, is what if we graph two lines, and it's tough to see here, but what if we graph two lines and the two lines end up what are called, or what is said to be coinciding. Coinciding means that they overlap, that they lie on top of each other. Well, what does that mean? Well, that basically tells us that the equations we end up graphing are the same line. We graph the two equations that are the same exact line. Okay, now the thing here, and this is kind of jumping ahead a little bit to geometry, is no matter where I look, if I choose any point along that line, both lines would have in common. So it doesn't tell us that there's no solution, but what that tells us is that there's infinitely many solutions. That no matter what, any value of x and y, I could choose, for example, 1, 2, or whatever that would be, any value of x and y that falls on that line would represent a solution. So there's infinitely many solutions. So that's what we're going to look at today. Being able to identify if there's no solution based on whether the lines would never intersect or if there's infinitely many solutions. So the way we're going to look at that is we're going to look at one through graphing, which graphing it's going to be either an intersection, parallel lines, or the lines will overlap. And we're also going to look at how do we solve them by substitution and elimination as well. So let's take a look at these special cases. All right, so once again here's what I want you to do. I want you to pause the video here. I want you to try these again. We did the first two examples. I want you to try in 3 and 4 on your own. So remember, first thing we want to do when we graph equations, we want to make sure we solve for y first. We want our equation to look like y equals mx plus b, what is called slope-intercept form. In order to graph it properly, we need it to have it in that form. So take a look at 3, take a look at 4. First thing, solve for y, get y by itself, and then graph. Okay, so I want you to pause the video here, pause it, work on these two problems, and we'll talk about the solution. Okay, after graphing the lines, here's what you should get. Looking at the first example, this one's already written in slope-intercept form, so graphed it right away. Y-intercept of -6, applied my slope of 3. Remember, when you see a whole number, that is 3 over 1. So I applied my slope of up 3, right 1, up 3, right 1, and applied it a couple points. Got the green line. Red line, I needed to move the 3x over to the other side, so I added 3x to the right side. I got 3x plus 1. So here I plotted my 1, I went up 3. My red line's a little bit off, but nonetheless, I applied my slope. Now I see here, okay, looking at our last table with our rules, we see that the two lines do not intersect. So what does that tell us about the solution? Well, if they don't intersect, that means they don't have a value of x and y in common. There is no value of x and y that those two lines share. So therefore, this means that there is no solution to this system. There is no value of x and y that they have in common. Okay, looking at number 4. Okay, my first line, y equals 4x minus 1, written in slope-intercept form. I can graph that right away. See, the green line's kind of the red line's already on top of it. So that one started at -1, applied my slope again. When you have 4, that means 4 over 1 is my slope. So I went up 4, right 1, up 4, right 1. The red line, not in slope-intercept form because I have -2y. So the first thing I did here, I showed it, divided by -2. Not added -2, or not added to, but divided because we were multiplying. Then I divided everything over here by -2, and I got 4x minus 1. Now quickly, if you look at these two equations, notice that they end up being the same equation. So when I graph the red line, notice how it falls exactly on top of the green line. Okay, so you got to ask yourself, what point do these lines have in common? Well, if you look at the points that I graphed, now they're a little off, but all the points, that one, and any point in between, both lines share. That means there's not just one unique solution, there is actually infinitely many solutions. Remember, lines continue on forever in both directions, so no matter what, any point that falls on that line would be a solution. So there, in this case, you have infinitely many solutions. So one, be able to recognize whether we have no solution or infinitely many solutions based off the graphs. Okay, so let's talk about how it looks like when we look at substitution and elimination. So number 5, I'm going to look at substitution. 6, we'll look at elimination. So follow along, I'll do number 5 with you guys. So we have -16x plus 2y equals -2. Remember, with substitution, I want one of my equations to say y equals or x equals so that I can substitute it in. I see my second equation, I have y equals 8x minus 1. So I'm all set to go. So in the other equation where I see y, I'm going to substitute 8x minus 1 in for y. So my first equation becomes -16x plus 2, and instead of y, I'm going to write 8x minus 1. That will equal -2. Everything else stays the same. Then if I distribute the -2, I have -16x plus 16x minus 2 equals -2. Okay, so what happens here? Well, we combine like terms. Notice I have 16x and minus 16x. If I add those together, -16 plus 16, what does that give you? That gives you 0x minus 2 equals -2. Well, 0x, there's no sense in writing that because anything, no matter what x is, anything times 0 is 0. So this term ends up dropping out completely, and what you're left with is -2 equals -2. Now, how do I determine what happens here? Well, we got to think. We either have no solution or we have infinitely many solutions. So which one would it be in this case? How do I know? Okay, the way I determine this is by the final result. Notice how I get -2 equals -2. Ask yourself, is that true? Yes, that is true. So does that mean no solution or infinitely many solution? So if the equation in the end remains true, if this is a valid statement, What that means is that this is infinitely many solutions, that any value, any point of x and y that fall on these lines would be a solution to both systems. So the way we're going to write this is infinitely many solutions. Okay, so that's substitution. Let's take a look at what happens with elimination. So now remember, with elimination, what we're going to try and do is we're going to try and eliminate either x or y. Our goal is to kind of get one of the variables to cancel out first so that we're able to solve for the other variable. So I look at this problem, I see negative 18x plus 6y. I have 3x minus y, so I want to get these to match. Now luckily I can take and match up 18 and 3 if I were to multiply this by 6. Same thing here if I multiply by 6. So what I'm going to do is I'm going to take the second equation and I'm going to multiply the entire thing by 6. Now that's going to give me 18x minus 6y equals negative 12. Okay? So I multiplied everything in the entire equation by 6. What I'm going to do is bring down the first equation since I haven't touched that. That is minus 18x plus 6y equals 24. Now what I'm going to do is I'm going to add the two equations together. And notice here, okay, boom, 18x minus 18x, that cancels out. That would give you 0x. 6y or minus 6y plus 6y, boom, cancels out. That gives you plus 0y. And that's going to equal negative 12 plus 24, that's 12. Well, what happens here? 0x, 0y, we don't write those. That's just 0. 0 equals 12 is what is left over. Now I look at this. Notice both variables cancel out. So that's a special case. Doesn't happen all the time. Both variables cancel. We only wanted one, and both ended up dropping out. And what you're left with is 0 equals 12. Now, as an equation, you've got to ask yourself, is this true? Does 0 equal 12? And the answer to that is absolutely not. 0 does not equal 12. So remember, does that mean no solution, or does that mean infinitely many solutions? Okay, so let's think for a second. Which one does that represent? Remember in the last example that we looked at, the equation held true in the end, right? And this one it doesn't. Last one, because it did, it was infinitely many. This one does not. It's not true, so it represents no solution. Okay, so when both variables drop out, the end result, whether the equation is true or not, is going to tell us if it's no solution or infinitely many solutions. All right, so that concludes this video lesson on special cases. So again, we're looking at what happens when variables cancel out when there's no solution or infinitely many solutions. All right, to finish you off here again, just like always, got you a little bit of a video to watch, so enjoy.
The thing I miss most about kids though is my music. That's what you're gonna miss the most, because I grew up a 80s metal guy. Yeah. You know, Metallica, you know. Ooh, ooh, yeah, New Bone Soldier, yeah. Love it, Dio. We're off to the witch. You know, all that stuff. We might never return. I can't listen to that in front of my little ones, and it's aggravating because nothing but kid music is awful. It's awful. Oh, the sky is blue and duh. Buzz, buzz, buzz. Yeah, all right, I got it. You know, we need some rock music to save children's music. And there's no reason like bands like Metallica and these guys should not be knocking. They all got kids. I don't need to hear new, amazing Metallica. So play some kid stuff. They'd be amazing. I think they'd be great. James Hetfield came out and get around, yeah! Ready, boys and girls? Yeah! Ooh, yeah! Yeah! Ooh! Had a farmer. Had a dog. Yeah! Had a dog, yeah! Bingo was his name, oh yeah! B-I-N-G-O. B-I-N-G-O. Yeah! Ooh, yeah! B-I-N-G-O. to you. Bingo, what's his name? Oh, hey! Bingo, what's his name? Huh? Yeah! Ooh, yeah! Ozzy would be great if London Bridge is falling down, falling down, falling down. London Bridge is falling down, my fair lady. And I mean, AC/DC would be the ultimate. They'd be the ultimate. I would give AC/DC row, row, row your boat, because they'd be amazing at it. They'd be amazing at it. Just come out, little Angus come out. And then Brian Johnson, another great front man coming out. You got to row, row,